Hi, I'm Ed Rushman, and this is a brief look at encryption. For those already an expert, please bear in mind that the intent here is to put encryption in student hands and spark interest. I'm not an expert in encryption, just enthusiastic about it. So what is encryption and what does it do for us? Encryption makes a message unreadable for anyone who doesn't possess the key. This is oversimplified. There's a lot more to learn here. Of course, this is great for passing secret messages. Businesses that process credit card payments use this to hide the credit card number. And the military has used encryption for at least 2,700 years. There's a few different methods that go way back in history that I'll show you right here. An encrypted message can be protected from change as well, provided it has a digital signature of some sort. More on that in another episode. The principles haven't changed, but computers allow huge messages to be encrypted quickly and in a way that can be impractical, not necessarily impossible, to break. Impractical means, practically speaking, you're not going to break it. For today, we'll use a symmetric key, the same for encryption and decryption, but there are also public keys, and you can look that up for further study. So here's what we need. We need an encryption tool. We need a message to encrypt. We need an encryption method. That's what the tool will use. We'll use AES-128 today, and it's the current standard that the U.S. government chose. A cryptographic key. Larger keys are more secure. Sometime I'll do just a whole thing on that. The ciphertext. Now that's the encrypted message. So you have your message, and once you encrypt it, that's called the ciphertext, the thing that results. And then the decrypted message, which is decrypting the ciphertext. Now it'll be the same as the message we encrypted if we do everything right. So here's a web page that allows us to demonstrate encryption. AES is a standard, and it's considered secure enough for top secret military communications, at least in its 256-bit form. 192 and 256, I believe, are both allowed for top secret. Messages are broken into blocks, and each block is encrypted. The message is scrambled in multiple transformation rounds. It's a little like making turns to a Rubik's Cube according to some set of directions. You could write letters on the cube, I suppose. The key would say which turns to make, and to see the original message, we would just reverse the steps in the key, making the cube look like it did originally. So you just do it backward to get it back where it was. That's kind of how the rounds in AES-128 work to scramble and hide the original message. If that doesn't make sense, don't worry. You don't need to know it to do some encryption. So let's go. First, let's go to the URL. Type in the message. The quick brown fox jumped over the lazy dog. Period counts as a character too. By the way, encryption treats data as binary, so it can encrypt a picture from a camera just as well. Any data can be encrypted. The mode is either ECB or CBC. CBC is newer and the better option, where the encryption of each block depends on the text that came before it. It's too much to explain now, but search for ECB versus CBC mode AES encryption to see an example and the details. We'll just take CBC. The key size is in bits, binary bits. If we type the key in hexadecimal, it would be 128 divided by 4, or 32 nibbles. Nibbles are 4 bits, half a byte. 1 nibble is 1 hexadecimal character. But this demonstration uses regular words, and they treat each letter as 8 bits, 1 byte, so that means 128 divided by 8, or 16 characters. You should know that characters are not necessarily really 8 bits. They could be 16, they can be 7, and all that. But for purposes of what we're doing here, that's the way it's going to work out. Think of the initialization vector as an added key, which it really isn't, but you can think of it that way. You can look this up for more detail. Again, there's going to be a few things you can go look up if you're really interested. I could go on like this for hours. I've typed in too many, see? So we will shorten this key, but remember that the key is binary. So for the output, you probably know hex is base 16. With the digits 0 to 9, then A, B, C, D, E, and F. Base 64 is an encoding into binary using 64 different symbols instead of 16. It allows us to show more data in fewer characters. So in base 64, the number 63 would be only one character. And you could show 64 in two characters. 64, by the way, in base 64 is 10. It's not binary, but it looks like it. But why can't it show the encrypted message using regular text? Because this is all binary, and although we typed in some text, the ciphertext, the encrypted version of the message, is a bit misnamed. It has to be binary, not text, and many binary values aren't printable. Some of my first jobs in computers, by the way, were reverse engineering binary data files. And if you want to know more about that, or compression, or hashes, leave a comment or get a message to me, and I'll make a video sometime. In fact, I'd love to hear what else interests you that you can't find already. I try to do things that somebody else hasn't done. Back to business, we'll use hex this time. Let's encrypt and see how it looks. Notice the result is a lot longer than our original message. First, it takes 2 hexadecimal digits to make a byte, and each character in the message is being treated as a byte. But if you count them, you'll often find the numbers don't add up. That's because this is a block cipher, and in this particular case, it processes in 128-bit or 16-byte blocks. So think of it as 16 character blocks, even though it's binary. What happens if we want to encrypt something that's 24 characters long? I mean, they're 16 character blocks, so that's either 16 or 32. So AES will pad the message out to 32 characters. It'll just add stuff. Except they won't be padding characters, it'll be padding zeros. And then it'll do the encryption. So it just fills it out with zeros, except the last byte in that 32-byte block. Sorry, yeah. It's hard to keep track of these numbers. Which is a count of the padded bytes so that AES can cut them off in decryption. We're getting in way too deep, but somebody was probably wondering, and I wanted to answer that. So now we move over to the decryption side. We'll just copy-paste the hex representation of the ciphertext into here. It's important that all our earlier choices match: the format, the mode, the initialization vector, which we didn't do, and of course the key. The format isn't really part of AES, but it needs to match here or else the binary values won't be the same. It's really just a way of getting us to those into that binary message. So let's decrypt. Now they only offer base 64 output on this site, but this output is still not our message as text. It's binary. We can decode the base 64 into regular text. And there it is. Let's go back and make the key wrong and see what we get. And we get this error. You can see how hard it would be to break this. The math involved makes many incorrect keys not even work at all. By the way, changing the base 64 a little can render the message unreadable too. Remember, it's just a binary representation in base 64, so it isn't easy to work with. Fortunately, we don't need to. I just wanted you to see what would happen. Now we're going to change just one character of the original key so that you can see that even a small change completely changes the ciphertext. That's a really important part of this, is to make sure that the keys and changing them a little bit doesn't give anybody any clues onto how it works. We'll copy the original ciphertext over here just so we can compare them. Not that we're going to do anything with that. See how much it changed? By the way, this is what happens if we try to simply decode the ciphertext. It's just garbage. that's enough for you to play with this a bit. Maybe try sending a message to someone using encryption. And if you want to get famous, figure out how to break it, how to decode these messages without knowing the key. That would be major. I'm Ed Rushman. I hope you enjoyed this. I look forward to your comments, questions, or corrections. Thank you.